I'm talking, of course, about the quantum computer. These far-out devices make the sickest gaming rig you can buy at Best Buy look like a cheap calculator watch from the 1980s. You know, as a reference for those few special people that think any gaming rig at Best Buy is good. We're talking processing power that could let you binge the entirety of Netflix's catalog in 0.000000001 seconds flat. A quantum computer could theoretically crack military-grade encryption codes that would take a normal computer longer than the age of the universe to solve. Now I know what you're thinking. Damn bro, building a quantum computer sounds harder than getting shredded abs and dating a Kardashian at the same time. Well, you're not completely wrong, but don't quit on me yet. This is some legit next-level sci-fi shiz that'll blow your pea-brains to the cosmic rafters. So let's get into it. Get ready to feel more disoriented than that time you took too many edibles at Coachella. We're going quantum. First off, we need to understand why quantum computers are such a game changer compared to the lame classical computers we use today. See, classical computers process information in bits. Those are the famous ones and zeros you've heard about. It's a basic, binary way of doing things, kind of like getting girls from your geometry class back in high school. They're either a 1 or a 0. Quantum computers ditch those sad, restrictive bits in favor of qubits, quantum bits. Thanks to the bizarre subatomic laws of quantum physics, these qubits can represent ones, zeros, or even terrifying combinations of both at the same freaking time. It's like your geometry girl can be both a smoke show and a gargoyle simultaneously. Okay, that's some straight up Dark Souls vibes. This freaky phenomenon is called quantum superposition, and it's just the first in a laundry list of bizarre quantum effects that gives these cyberpunked out qubits vastly superior computing capabilities over lame old bits. With enough qubits, you've got computing power that grows exponentially. And I mean exponentially. Like, if a normal computer is a cheap Bic lighter, a quantum machine is the freaking sun. We're talking potential for solving problems in hours that would take classical computers quintillions of years. Alright, at this point your heads are probably feeling pretty spun out already. Well, put on your quantum safety goggles, kids, cause shit's about to get real weird from here. So, if we want to build a quantum computer, step 1 is getting those funky little qubits, right? Easy peasy, right? Wrong! Making stable, reliable qubits is kinda like trying to knit a freaking sweater out of atomic particles. You're working at a scale so small, a simple sneeze could ruin the entire operation. We're talking distances less than the width of a few atoms here. It's maddeningly precise. Most physicists get their qubits from exotic sources like ultra-cooled, gaseous atoms or particle defect impurities in super pure crystals. You have to create these wild setups using things like laser technology, maglev tracks, and high-powered vacuums, isolating the potential qubits from even the slightest external interference. If I had to describe it, it's kinda like trying to keep a soap bubble intact while madmen are blasting it with hairdryers and screaming into its non-existent ear holes. Stable qubits can only survive under the most artificial, extreme environments. But getting your precious little qubits is just half the battle of this wild quantum rodeo ride. So, you've managed to isolate some ultra-pure, frigid atoms and zap them into qubit mode using cosmic lasers or whatever. Congrats, you're officially the most bougie hipster in the lab. But trust me, your quantum struggles are just beginning. For your little qubits to be useful for actual computing, you need a whole bunch of them in something called coherent entanglement. Did that sound like a paradox to you? Yeah, it's next level weird stuff. Having multiple qubits in a coherent, entangled state means their quantumly uncertain properties have become interwoven and linked on a subatomic level. It's like they're all doing an ultra-microscopic can-can kick line. The more entangled qubits you've got, the more powerful your quantum computations. Ah, but here's the catch. Literally anything in the external environment can disrupt this delicate quantum dance troupe and destroy their coherence. We're talking even the faintest electromagnetic fields, thermal radiation, or nearly subatomic particles. It's so preposterous, you basically have to create a perfect vacuum void of literally any environmental interference. You need shielding that's 1 million times better than the stuff protecting modern silicon chips. One stray electron or quirky sound wave and poof, there goes your quantum magic. And this is why those crazy eggheads have had to come up with stability tactics like operating everything at temperatures just a smidge above absolute zero. You're working in the most sterile, isolated, frosty environments known to humankind. Some of that hardware looks wilder than anything from Interstellar or the craziest of Elon's fever dreams. And he's got a lot of them. So if you're starting to sweat just thinking about all the difficulties of maintaining quantum coherence, don't feel too bad. The pioneers of quantum computing have sobbed cold, frustrated, arctic tears, overcoming this largely with brute force trial and error. One notable name in the game is D-Wave Systems. These intrepid Canadians have raised over $200 million to build specialized hardware for sustaining coherence in superconducting circuits, thus enabling quantum calculations. I mean, hey, it's only fitting that Canadians be involved in such a frigid field of science. A key component they use is something called ion traps, which is just as wild as everything else we've talked about. They use magnetism to actually suspend atoms in an electromagnetic force field, then blast them with lasers to isolate the quantum properties. It's like a microscopic nightclub run by subatomic particle ravers, or more accurately like forcing specific atoms into a quantum straitjacket. All of this effort has allowed D-Wave to produce limited prototypes of quantum annealers and computers for organizations like Lockheed Martin, NASA, and Volkswagen to test out. And the big G's over at Google have even experimented with their own quantum hardware, leveraging similar techniques. And yet, despite all that money and brainpower, these systems are still miniature proof of concepts, nowhere close to realizing quantum computing's true game-changing potential. The current gold standard taps into one of the best mechanisms for maintaining quantum coherence: nuclear magnetic resonance using ultra-pure, artificial crystals. This tech is how companies like IBM and Rigetti are gradually building larger, more robust quantum systems. But even they've only coaxed a couple dozen qubits to cooperate in commercial hardware so far. Suffice to say, the challenges of engineering reliable quantum systems at a practical large scale is something that makes the Wright brothers' achievement at Kitty Hawk look like, well, kind of a warm-up, really. Now look, even with the massive scientific and engineering challenges involved, there's no need to completely crush your excitement for the quantum computing revolution. While a universal, civilization-redefining quantum computer is likely still decades away, the fledgling progress being made right now is indisputably shaping all sorts of technological frontiers. Quantum breakthroughs are already radically advancing our grasp of cryptography, artificial intelligence, materials science, pharmaceuticals, logistics, and more. Even the kinda clunky explanation of qubits and quantum phenomena here has hopefully illuminated why studying this granular realm could unravel some of the deepest mysteries of physics itself. Just being able to manufacture reliable qubits and sustain entanglement is forcing us to innovate technologies like nanoscaled magnetics, photonic circuitry, cutting-edge vacuum engineering, cryogenics, exotic materials, you name it. It's like the Apollo program for fundamentally new scientific domains. And while primitive, the cloud-based quantum machines from IBM, Rigetti, IonQ, and others are finally allowing anyone to really test out quantum algorithms for the first time in history. Students, developers, researchers, all getting hands-on experience with potentially world-changing capabilities like quantum machine learning, chemistry simulation, optimization mappers, and secure communications. There are legitimate possibilities that we unlock elemental discoveries, allowing things like quantum teleportation of information, incredibly advanced AI models, transporting data at light speed, or even peering into an alternate universe. Hell, maybe even time travel one day if the theories prove out. We're on the frontiers of realms and realities our silly human brains can barely comprehend or even envision right now. Of course, before we can expect revolutionary applications of quantum computing to really reshape industry and society, some monumental engineering hurdles still have to be overcome. As I mentioned before, getting dozens of qubits to harmonize in an incredibly precise quantum cycle is just the tip of the iceberg. To unlock exponential computing capabilities, quantum systems will likely require thousands or even millions of qubits all operating in a massively entangled state without a single glitch or hiccup. That's like asking all 7 billion approximate people on Earth to simultaneously perform flawless, synchronized dance moves in silence at the quantum scale. I can barely do a tango with another person, let alone something like that. There's speculation that entirely new systems like photonic quantum circuits or exotic mediums like topological superconductors could enable bigger quantum leaps in the field. Maybe we employ wild technologies harvesting qubits from subatomic particle collisions or cosmic rays from an endless supply of raw materials. Or perhaps some genius will finally crack the code of those theoretical quantum biological computers some scientists think may naturally exist within the molecular machinery of human cells and certain proteins. Wouldn't it be trippy as heck if we finally realized our own bodies have been low-key quantum computers this whole time? I mean, if you're Tony Stark, it probably wouldn't be a big deal, but for the rest of us, hell yeah! Whatever breakthroughs eventually deliver the first scalable, general-purpose quantum computers, you better believe it's going to spark shockwaves as paradigm-shifting as the microprocessor revolution, the internet age, or heck, maybe even the original discovery of fire itself. So, as difficult as constructing large-scale quantum computers undoubtedly will be for us lowly Homo sapiens, the ultimate universal knowledge that pursuit stands to unlock may just render all that effort the most profoundly meaningful and important thing our society has ever done. I mean, it's either that or we just get really good at factoring large numbers and upset a bunch of encryption dudes. But come on, what's the fun in thinking small like that? Let your quantum-addled consciousness dream a little bigger, bro. Who knows what magic you might unlock? If this brain-breaking journey into the quantum realm has you ready to grab your own ion trap and start lassoing individual atoms, why not channel that excitement into absolutely crushing the like button, sharing your most mind-blowing quantum revelations in the comments, and smash and subscribe for more wild rides to the edges of scientific understanding.